let's look at the way that text is encoded in files and in RAM. We are going to, in this video, cover how text can be encoded using the ASCII approach, and we'll also look at UTF later on, as you'll see. But first, let's just try to keep things simple and write a string of characters which makes up words that have a meaning for us. Now, outside of the computer world, we have this alphabet that we use with letters, uppercase letters, punctuation signs. But as far as a computer goes, it has to be encoded using binary values. The ASCII encoding is a 7-bit encoding scheme, where there is an 8-bit, as we'll see fairly soon, but there is this set of 127 characters starting at 0 and going all the way to 127, which includes all of the uppercase characters and the lowercase characters, as well as the digits that are right here, and the most common other characters that we use, such as a space. So if we look here at Hello World, as far as a computer goes, the uppercase letter H is the decimal value 72, but it's the hexadecimal value 48. And if you don't believe me, you can always go into your ASCII table and find that the hexadecimal value for H is indeed the hexadecimal value 48. Now we can play this game and actually map each of our character in our string. So this one is 6-5, and a L is 6C. The other L is 6C. The O character is 6F. The space is 20. The W is 77. And it's followed by 6F, which is O. 72, which is the R. 6C, which is an L. D is 6-4, and finally the exclamation point is 2-1. Okay, now I'm careful here not to call this 77, because this is not a decimal number, it's an hexadecimal code. So I call it 77. Now, each of these characters requires a single byte. Okay, so we're going to expand here on 6F, which is the character lowercase o. Okay, 6F is made of 8 bits. Since it's 1 byte, we get 6 and we get F. Now F is the last character in the hexadecimal encoding, so it's actually 1, 1, 1, 1, and 6 is 0, 1, 1, 0, so 0, 1, 1, 0. So this is the 1 byte of data that is required to encode the character O in the string hello world. You see there's another O character like this. Now I'd like to emphasize that 1 byte, okay, is 8 bits, contain 8 bits, and 8 bits has 2 to the 8 different possible values, which gives us 256 possible characters. I told you that the basic ASCII encoding had 128 characters from 0 to 127, and the second half of the range is occupied from 128 to 255 by all sorts of weird characters that are not commonly used in most email or web page encoding. The problem is once we start thinking in terms of using extended characters, so characters that do not belong to the standard Western character set like this. We need to have much more than 256 possible characters. So one trivial solution is to simply encode each characters in our encoding with more bytes. Okay, so for example, a commonly used size for a variable is the 32 bits, which gives us a very large quantity of possible characters. This is 4 bytes, like this. And if we wanted to encode the lowercase o, or 6f in 4 bytes, what we essentially would need to do is to take our 0 encoding, our O encoding like that. This is 1 byte. 1, 2, 3, 4, 1, 2, 3, 4. That's our second byte. 1, 2, 3, 4, 1, 2, 3, 4. That's our third byte. And finally 1, 2, 3, 4, 1, 2, 3, 4, our fourth byte. So as you may notice, now we have the ability to encode millions of characters by using 32 bits of data. But for most character that we need to write emails and encode the content of web page, we would be wasting, about 3 bytes of data for each byte of useful information. So there is a need to have a system that has the flexibility to encode a very large number of characters, which includes all of the kanjis in the Chinese character, both the traditional and the simplified, but be efficient enough that when we are expressing Western text, that it can be done in a smaller number of bytes. And this is where our UTF-8 code is entering into play. So let's just move on to our next slide right here. The UTF-8 is a variable width encoding system, which is the de facto standard on the internet. And the way that you can do variable encoding is essentially by adding information to the bytes of information, which is going to cue the decoder that some bytes are actually part of a larger number of bytes to encode a single character. So the first case for UTF, case number 1, is all the character from 0 to 127. Okay, these are the characters that are included in the ASCII range. Okay, the singular property of these characters is that all of their binary encoding, 2, 3, 4, are beginning with a 0. So any bytes that begins with a 0 is essentially going to be a single byte character in the UTF-8. And in one way, UTF-8 has the ability to read most of the ASCII encoding, because these characters in ASCII and in UTF-8 are actually using the same byte pattern. Now things becomes a bit more difficult in the second case, where the range is beyond 0 to 127. What needs to be done in case 2, which would be 128 and above, okay? What needs to be done is you need to build into your binary encoding enough Q that the decoder is going to be capable of telling, when it begins reading, that the next character is occupying more than one byte. And this is done using some structural bits. So I'm going to change here, and I'm going to use a different color for the structural bits. But in a case where we have a 2-byte character, okay, the cue is that the first byte is going to have 2 1 followed by a zeros. That's 3 character, 4, 5, 6, 7, 8. And the leftover characters are actual data. And the following byte, which contains the rest of the data, 4, 5, 6, is going to begin with a 1, 0. Okay, so when an UTF-8 decoder sees a byte that begins with a 1, it knows that it's not in the ASCII range, and therefore it is part of a multi-byte characters. So the number of 1s at the beginning of this followed by a 0 is going to tell the decoder, okay, this character is going to be taking 2 bytes. And to confirm that there is no mistake, each byte that follows on has a 10. So in a 3 bytes character, the encoding is quite similar. You have 1, 1, 1, 0, data, 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 data. Okay, so the cue now is 3 1s in a row followed by a 0, then 1 byte, 2, 3, 1, 2, 3, and finally the third byte with 6 more data bytes. Okay, so we are going to make to use a specific character as an example here. I'm going to use the Euro character, and pardon me if I butcher the Euro character right here, but its UTF code is 20AC. Okay, so the U plus is simply telling you that it's a Unicode denomination, and it's expressed in binary encoding. Now if you look, we can translate, so a 2 here in binary is going to be 0, 0, 1, 0. That's our 2. A 0 will be 4 zeros in a row, and A is 1, 0, 1, 0, 1, 0, 1, 0, and finally a C is 1, 1, 0, 0, 1, 1, 0, 0. Now if you're not sure as to how binary characters are working, then you should review the textbook, the lectures, or the movie on the topic. Now you want to encode this long string right here as a number of bytes. Okay, the punchline is that ultimately the Euro symbol needs 3 bytes. So the first thing that will be needed to be done is to place your structural bits right here. We'll need 3 bytes followed by a 0, and 1, 2, 3, 4 data character. We'll have a second byte with 6 data character right here, and finally a third byte with 6 more data character. Now I'm going to revert back to red. Okay, and the way that the data gets encoded is you take the first 6 character, 3, 6, and you place them right here. So 1, 0, 1, 1, 0, 0. And then you take the next 6 character, which is 3, 0, 4, 0, a 1, and a 0. So 1, 2, 3, 4, 1, 0. So this is the range that goes here. And finally the last 4 digits, binary character 1, 0, 0, 1, 0. So when the Euro symbol gets encoded using UTF and put into a file, 3 bytes are going to be used. The first byte will be this one, byte number 1, byte number 2, and byte number 3. When the text gets opened by a text editor, it has to know that it's a UTF encoding, and as the encoder will proceed from byte to byte, as soon as it reads this byte, it'll first say, oh look, there's a 1 at the beginning of this byte, so this is not a case 1 character, this is not a ASCII character. So let's count. 1, 2, 3. There are 3 bytes incoming right here. This is our padding. And that also means that in the following byte, the 1, 0 will be ignored, the 1, 0 will be ignored, and the data is going to be reconcatenated. So 0, 0, 1, 0 coming from here, plus 0, 0, 0, 0, 1, 0, okay, which comes from here. And finally 1, 0, 1, 1, 0, 0, which is the data coming from here. If you take this value right here and you have 1, 1, 0, 0, that's a C, 1, 0, 1, 0 is an A, 4 zeros in a row is a 0, and this is a 2, we are recovering the original encoding for the euro. Okay, so the trick, the magic trick here is that in order to get the variable length character encoding in UTF-8, some bits inside of the bytes are inserted to let the decoder know of what is going on. This is how it is possible to use 4-byte when we need 4-byte, 3, or when there's no need to use more than 1 byte, you can simply use the encoding the same way as ASCII. I hope that this explanation is useful. Good luck.